Hello everyone, my name is Lorenzo Leonetti and I'm from University of Calabria in Italy. The work I'm going to present is about a novel two-scale cohesive finite element model for the investigation of transverse cracking and induced delamination in fiber-reinforced composites. My co-authors are Professors Fabrizio Greco and Paolo Lonetti and Doctors Daniele Gaetano and Paolo Nevone Blasi. Well, let's start with the motivation of this work. As is well known, fiber-reinforced composites may experience several failure mechanisms ranging from transverse cracking to fiber breakage. In order to simulate such damage events, both phenomenological and micromechanical approaches have been proposed in the literature. This introductory slide presents a rapid overview of the most used multiscale modeling approaches for simulating transverse crack propagation in fiber-reinforced composites. Classical nonlinear homogenization approaches, in which a one-way coupling is established between the micro and macro scale, are very efficient but in general not suitable for handling strain localization. To this end, enhanced computational homogenization approaches have been introduced. In particular, strain gradient and discontinuous approaches have been widely used by virtue of their capability to introduce a length scale into the overall constitutive response. However, one of their main drawbacks consists in their high computational cost. Some years ago, our research team had already proposed a multiscale model belonging to the class of computational homogenization approaches, which was limited to a single propagating crack and therefore unable to simulate the transition from a diffuse to a localized damage state. Instead, in the present work, a more efficient two-scale cohesive finite element model is proposed based on a combined continuous-discontinuous hierarchical homogenization in which the macro and the macro scales are only one-way coupled. The proposed continuous-discontinuous nonlinear homogenization is performed on a properly identified repeating unit cell, which is representative of the assumed periodic composite microstructure. The other hypotheses of this model are perfect separation between micro and macro scales, quasi-static loading conditions, small deformations, damageable fiber matrix interfaces, and breakable matrix, modeled as a collection of cohesive elements embedded in a continuous phase. Thus, also assuming periodic boundary conditions on the unit cell, a hierarchical homogenization scheme is applied with the aim of deriving the overall nonlinear response of the composite. To overcome the well-known ill-posedness of the homogenized maker continuum problem in a softening regime, a further homogenization is performed at the interface level as a post-processing step. In other words, the discontinuous part of the numerically derived overall constitutive response is obtained by extracting the portion of the loading curve after the appearance of a macroscopic localization band. Finally, a homogenized traction separation law is derived after suitably defining the microscopic cohesive traction vector and the macroscopic displacement jump. The main advantage of this approach is that a global traction separation law is derived through offline computations in a very efficient manner. In the present multiscale approach, multiple cracking at both the microscopic and macroscopic scales is accounted for by adopting a cohesive volumetric finite element approach. The underlying variational formulation assumes the constitutive behavior of embedded interfaces as the unique source of nonlinearity. It is worth to highlight the presence of an additional contribution in the resulting weak form, which represents the virtual work of the traction transferred by the embedded interfaces. In order to reduce the well-known artificial compliance associated with the adopted intrinsic cohesive approach, a micromechanics-based stiffness calibration methodology recently proposed by some of the authors is used in the present work. Well, the overall stress-strain response up to localization and the homogenized traction separation law have been computed by using a finite element procedure able to follow the principal path of the analyzed unit cell, in combination with subsequent coupled macroscopic stability analysis for the detection of the macrostrain localization, which involved the solution of 3 independent linear perturbation problems at each loading step. Finally, a post-processing step is performed to extract the homogenized traction separation law from the micromechanically derived stress-strain relation. In order to automate all these sequential computational tasks, an ad hoc MATLAB code has been used within the commercial environment COMSOL multiphysics. This part of the presentation is devoted to the numerical experiments carried out to assess the reliability of the proposed multiscale model. The considered case study is a tensile test performed on a fiber-reinforced laminate made of stacked aluminum and glass epoxy prepreg layer, which is known as glare. Here, the elastic properties of the microconstituent are shown, as well as the inelastic parameters of the embedded cohesive interfaces used to simulate fiber matrix debonding and matrix cracking. The considered microstructure for the prepreg layer is made of 60% fibers with diameter of 10 microns and distributed in a regular hexagonal arrangement. Such a microstructure can be generated by the repetition of this rectangular unit cell. Then, the geometry of the simulated portion of laminate is shown, together with the mesh configuration adopted for the multiscale analysis. In particular, the mesh adopted for the prepreg layer is a mapped mesh with duplicated nodes, such that zero-thickness interfaces with homogenized cohesive properties are pre-inserted along the vertical mesh boundaries. Firstly, we present the offline computations performed on a given repeating unit cell to derive the bulk nonlinear response. Here you can find the related numerical outcomes in terms of both undamaged and damaged homogenized moduli tensor. In particular, the damaged moduli are derived by assuming an isotropic damage evolution function, which is directly extracted from the homogenized uniaxial stress-strain curve obtained from the principal path solution. This slide presents the additional results obtained from the macroscopic stability analysis performed at different loading steps, starting with the incremental moduli. These moduli are used to compute the acoustic tensor, thus allowing the rigorous derivation of the strain localization onset condition. This condition identifies the critical displacement jump by which the homogenized traction separation law is shifted to the left in order to extract its pure softening behavior. The previously mentioned offline computations have been performed for deriving three different databases. That is, a damage evolution function database for bulk homogenization, an incremental moduli database for the detection of strain localization onset, and the traction separation law database for cohesive homogenization. Please note that the present databases are only valid for a given microstructure, so that they must be recomputed in case of different geometries and moduli contrast, as shown in this slide, where the incremental moduli and the homogenized traction separation law are derived for different values of the fiber volume fraction. After performing the previous offline computations, a macroscale analysis of the considered laminate, here referred to as multiscale numerical simulation, is performed by using as material inputs the previously derived databases. The macroscale response is here reported in terms of global stress-strain relation and homogenized secant longitudinal modulus of the prepreg layer as a function of the applied strain. As a validation step, the results of this multiscale analysis have been compared with the outcomes of the fully microscopic analysis denoted as direct numerical simulation. In this analysis, taken as the reference, all the microstructural details are explicitly modeled, and both fiber matrix debonding and matrix cracking are included in the same way as in the repeating unit cell analysis. On the one hand, the good accuracy of the proposed method is demonstrated by the very small percentage errors on the initial stiffness and the peak strength of the prepreg layer. On the other hand, its notable computational efficiency is attested by the very high ratio of about 75 between the number of degrees of freedom for the reference direct analysis and that for the present multiscale analysis. As a further assessment of the reliability of the proposed modeling approach, a mesh sensitivity analysis has been performed by considering three different mesh configurations in the prepreg layer. The related numerical results have shown a substantial mesh independence, especially in terms of effective longitudinal modulus. In conclusion, a novel two-scale model has been presented, able to accurately predict transverse cracking and induced delamination in fiber-reinforced composite materials. This model adopts an inter-element cohesive finite element methodology for the numerical simulation of multiple cracking at both micro and macro scales. As the main ingredient of the proposed two-scale model, a very efficient offline homogenization approach is introduced for the bulk and cohesive interface constitutive behaviors. Then, the numerical accuracy and the computational efficiency of this model has been demonstrated by performing suitable comparisons with direct numerical simulations. Finally, a mesh sensitivity analysis has been reported to demonstrate the mesh size objectivity of the present results. Thank you for your attention.